In today's short video, we're going to take a look at the compounds that contain alkynes. These are a functional group that contains a carbon-carbon triple bond. In this video, we're going to take, again, a brief look at these. These are quite rare in nature. They're not often found in drug molecules because this triple bond is quite reactive. But we do need to go through a little bit in terms of the structure, reactivity of these. So, just to remind ourselves, we talked about this a little bit in a prior video when we were talking about the shape of molecules. Because the carbon-carbon triple bond has a structure where we essentially have one electron cloud kind of over here to this side, and then the electron cloud of the triple bond is here. The shape of these is 180 degrees or linear. All right, so real briefly in terms of nomenclature, alkynes are named with the YNE suffix. So just like we would name an alkene, we would number the chain to give the carbon-carbon triple bond the lowest possible number, and then any substituents. In this case, it's a relatively simple molecule. This is a butane derivative, but we're going to change the ANE ending to YNE. Okay, so this is the compound called butane. Again, not butane, but butane. And we would need to put a 2 in front of this just to indicate the position of where the YNE, or the triple bond, was actually occurring. So that's about as far as we're going to go with alkyne nomenclature. You might see some other complicated ones, but the rules are very, very similar to alkenes. When it comes to the actual structure of this triple bond, what exactly is this? So what are we representing with these lines? So let me sort of zoom in on this molecule. And let's take a look at the types of orbitals that are actually involved in these 3 lines that we represent here. So recall when we were talking about alkenes that we had 2 types of orbitals that were overlapping. Okay, here we have what's called a sigma bond. Okay, and this is a sharing of 2 electrons in sort of a head-to-head overlap, like we saw in the alkenes. However, with the alkynes, the triple bonds, we not only have a set of these pi dumbbell-shaped orbitals in the plane defined by the board. Okay, that would be the so-called XY plane, if you would. We also have an extra set of pi bonds. They're going to be sort of orthogonal to this, or coming in and out of the blackboard here. So you could represent those like this. Okay, now it could be a little bit hard to visualize this. What I like to think of, if you were to center on one of these carbons, think of Cartesian coordinates. Okay, you probably recall from geometry, you have the x and the y. Okay, but in 3-dimensional coordinates, you also add a z-axis that's then perpendicular to that. So these carbons now have an axis that involves a sigma bond, and then it's going to have 2 of these pi bonds, one in the plane of the board, and then one that's orthogonal or perpendicular to the board coming in and out. So in essence, these carbon-carbon triple bonds are twice as reactive, if you will, as a carbon-carbon double bond, because there are 2 sets of these pi electrons that are available for reactivity. So in the next section, let's just take a look real briefly at the reactions that these can undergo. Hi, welcome back. So let's just take a look at some of the reactions that alkynes can undergo. And because of the nature of those 2 pi bonds, we're going to end up having to use 2 equivalents of whatever reagent we're going to react with the triple bond in order to get it to fully react. So let's take a look at this compound and see what it would give me if I use 2 equivalents of Br2, 2 equivalents of HCl, or 2 equivalents of water with an H+ catalyst. Now, the reagents that you can use with an alkyne are the exact same reagents you could use with an alkene or a double bond. So recall we could use the X2 reagents, so things like bromine or chlorine or hydrogen with the metal catalyst. Or you can use the HX reagents, things like HCl or HBr, or the hydration reaction like water. Now I've chosen this specific example just to demonstrate that alkynes also follow Markovnikov's rule. So let's just jot that down. And I'll just abbreviate Markovnikov's rule as Mark's rule. So for this first one, we actually wouldn't need to apply Markovnikov's rule because this is a symmetric, or I'm sorry, the reagent itself is symmetric. But the product we would get out would look like this. We would end up putting bromine on the 2 carbons of our alkyne and completely eliminating the 2 pi bonds. Again, this does require 2 equivalents of reagent. So in this case, we would get, let's see, this would be 1, 1, 2, 2, tetrabromobutane would be the final product there. Now in this case, we do actually have to apply Markovnikov's rule. Remember, when you're adding an HX reagent, the X group, in this case chlorine, is going to add to the more substituted carbon of the triple bond. So here we have this carbon has, not only this carbon as a substituent, but this one over here. So this is a di-substituted carbon. This one only has 1 carbon substituent, so it's a mono-substituted. So the X group should add to the 2 position of our 1-butyne. Okay, so let's just draw out the structure then. So in this case, my chlorines are both going to add to the carbon that is more substituted in my original compound here. So I would end up getting 2, 2 dichlorobutane as my product. Lastly, let's do a hydration reaction. And this is essentially a double hydration because we're using 2 equivalents of water. Just like the above example, my OH groups are going to both add to the 2 position in this case, and I would get a diol compound that are both substituted on this position where I had the higher substituent in my alkyne. So that covers the basics for alkynes. Again, they are a fairly important group for synthetic organic chemistry, but not as much for biochemistry. These are so reactive, they're very, very rarely found in nature, and only a few classes of drug molecules actually have this. But it is important to be aware that they do exist and that they do undergo reactions very similar to alkenes.